Here we're going to review some things you probably learned in grade school about ecosystems. There's three major components of the biotic part of the ecosystem. The producers. The producers are the plants. On land and in the water, producers would be what we call the phytoplankton, unicellular, photosynthetic protist, and algae, and even photosynthetic bacteria. So the producers are the ones that produce the food for themselves, but for the consumers as well. The consumers eat the producers, and they also they can eat other consumers as well. And we always tend to forget very important decomposers, fungi and bacteria, that break down the dead organisms and the waste matter into nutrients that the plants can use and that they can use as well, the decomposers. Another name for producers are autotrophs. Troph means food, auto means like automatically. So they automatically make their own food by photosynthesis usually. So this is what I said, the phytoplankton are the unicellular algae and protists that are photosynthetic. Not only do the producers produce food, they also produce oxygen that is important for the consumers and the producers to do respiration, that is to get the energy out of the glucose. So again, you learned this in semester 1 of biology. It's the producers have chloroplasts. They're organelles that absorb sunlight and use that sunlight energy to store energy in the bonds of glucose, which they form from carbon dioxide and water. And then they emit the waste product, oxygen. And the glucose, in turn, is what's eaten by the consumers and the plants as well, the producers as well. And in the mitochondria organelles of the plants and animals, anyone who does respiration, oxygen is usually used to extract energy from the glucose and turn it into ATP and carbon dioxide and water. The carbon dioxide, of course, is then reused by plants to make more glucose. Producers, again, are called autotrophs, but consumers are called heterotrophs. They cannot make their own food. There's different types of consumers depending on their diet. So herbivores are consumers that only eat plants. That's all they eat. Omnivores eat both plants, animals, and fungi. We're omnivores. Carnivores kill and eat animals primarily. Scavengers eat dead animals, dead things. Fungi. When I think of scavengers, I think of like earthworms, vultures. Detrivores are like scavengers, but they're bacteria and fungi that decompose once living material, could be an animal, it could be a plant, it could be anything that's organic. Again, the decomposers and the detrivores are essential because everything that's living dies eventually, and we'd be buried under miles and miles of dead things. Or we live on top of miles and miles deep of dead stuff if it wasn't decomposed by the decomposers and detrivores. Decomposition releases carbon dioxide because most decomposers use respiration to eat the food that they do. But they also return the nutrients to the soil. So that's very important because plants need those nutrients. So an ecosystem, energy and nutrients flow through that ecosystem. Let's just look at energy first of all. So energy comes primarily from the sun. That's where it all starts. If the sun went out, plants couldn't photosynthesize. They couldn't make glucose, and since all the consumers depend on that food, they would all die off. So the sun is the source of all energy that goes into an ecosystem. Okay, so the plants, let's do a color red for that. So energy comes from the sun, is stored in glucose chemical bonds. Consumers eat the glucose and turn it into ATP energy. And then when the consumers and the plants die, that chemical energy in their bonds is released by oxidation in decomposers. And then what happens to that? It's released as heat. Actually, it's released in every interaction when heat flows. Some of that energy is lost as heat, of course, as respiration occurs. And heat after decomposers, it just leaves. All this heat just leaves. So energy is not recycled. Energy flows through a system, but energy is not recycled. That's an important point. So it's important that you realize that energy does flow through an ecosystem, but with every flow, a lot of its loss is heat. And that heat eventually cannot be used. It escapes the atmosphere eventually into space. So the sun has to always be there because the whole ecosystem would die out if the sun were not there to supply the energy that powers photosynthesis. Okay, let's do the nutrients, the actual elements that flow through the ecosystem. So, of course, all the elements flow through the ecosystem as they're made, as they're eaten, as they're pooped out, as animals and plants die. All those nutrients, food molecules, are recycled. They flow through the system, but they're also recycled. You don't have carbon dioxide disappearing like energy does. You have it being, you have the carbon dioxide being changed into other molecules. But atoms of every element, they don't change. What you start out with on Earth, you end up with on Earth. So it's important that you realize that elements or atoms are conserved, are recycled in the biosphere. I could say in an ecosystem, but same holds true for biosphere. Okay, so let's do some review questions. Some animals are called producers. No. Producers have to automatically make their own food. Autotrophs is another word for producers, and no animal makes its own food. So that's false. Herbivores, omnivores, and carnivores. These are all types of consumers. Phytoplankton, the photosynthetic protists and algae in water, plants and trees are plants, are producers. They're autotrophs. As opposed to consumers, which are heterotrophs, just to remind you. But the answer is these make their own food by photosynthesis, so they're producers. Carnivores primarily eat meat. They eat other carnivores. Well, they could, but anything, but not producers. They don't really eat that much unless they can't find food. They're not going to. I mean, if they can't find animals to eat, they'll eat what they can to stay alive, but they primarily eat animals. Animals could be herbivores are a type of animals, and carnivores, I mean, they can eat other carnivores as well. So I would say B and C, because they're both animals, and carnivores eat animals. Omnivores eat anything. They can eat plants, they can eat animals, they could eat carnivores, anything. That's us. So all of the above. Producers primarily eat. They don't eat anything. They make their own food. They're plants. No. The Venus flytrap is a plant that eats flies. Gets some proteins from snapping their flower down on flies and trapping them and then dissolving them. But that's outlier. Decomposers are important because they make soil nutritious for other organisms. Yes, they recycle the nutrients in dead things that were once living, and in the poop, the waste products, and the urine, they break that down into useful nutrients for plants. So that's true. So specifically for plants, but then indirectly for us, because then the plants, we eat the plants, etc. I'm sure you've seen food chains, which are in grade school, which are diagrams showing who eats who. So usually the sun's not in food chain. That's kind of obvious. So, the thing that the arrow is pointing to is who eats the thing before it. So grass uses the energy of the sun. Grasshoppers get their energy from grass. Energy and nutrients. Shrew eats the grasshopper, so the arrow points to the shrew. So the owl is pointed to by the shrew. That means the owl, go backwards, the owl eats the shrew. Or you can do, the direction of the arrow is who is eaten by who. So the grass is eaten by the grasshopper. So get that straight. Now, a food chain is just linear, but a food web is more accurate, showing the different things organism can eat in the ecosystem. So it's really more of a tangle of arrows rather than a food chain, and we call that a food web. Now, notice on the food web, they leave off totally the decomposers, which really is a very important part of the food web. Everything would point to the decomposers, and it would make a really messy diagram. Okay, so this energy pyramid is symbolizing the amount of nutrients and energy stored in each of the different organisms in an ecosystem, except for the decomposers. So we have at the base of the energy pyramid showing that it has the most energy available. It's like a pyramid. So the base is bigger. It has more energy and nutrients, not just energy. Energy and matter. So that means also if you weighed all this stuff, the producers will, if you gathered all the producers together, they would weigh more than the next trophic level, the herbivores, which would weigh more than the omnivores, the next trophic level. So each of these guys is called a trophic. That means eating level. Trophic. Not tropic, trophic. Okay, so we got the producers at the base of the pyramid, and then above that trophic level are the herbivores, the consumers that only eat the producers, and then we have the omnivores that eat everything below it, and then we have the carnivores that eat the omnivores or herbivores, because herbivores are animals too. So notice how if you had all the eagles and you weighed all the eagles in an ecosystem, it would be much less than the weight of all the insects in an ecosystem. So like I said, as you go up the pyramid, you get less available energy for the next trophic level. So as you go up, you get decreasing biomass, and you get less energy available, and you get fewer numbers of organisms because there's not enough energy in the trophic level below for them to get to be a big population. Now, this is very important. It's called 10% rule. 10% about of the available energy stored in the trophic level below another trophic level. Only 10% of that energy stored in the chemical bonds of those organisms is used, is available, becomes the energy in the organisms in the next higher trophic level. So you lose 90% of the energy as heat. So that's why you can't have equal number of organisms in a higher trophic level as you have in a lower trophic level. Look at this energy pyramid. So primary producers, okay, I can't think what a secondary producer would be, seriously, so I just call it producers. Primary consumers are the ones that eat the producers. Then secondary consumers eat the primary consumers. And then tertiary consumers eat the secondary consumer. That's kind of a better way than to classify them, rather than herbivore, omnivore, and then carnivore. I like this way better. Okay, but look at the numbers. J means joules, and that's the unit of energy that we use in science, like calorie, but it's a metric unit. I just noticed they made an error here. First of all, joules is a unit of energy that we use in science. And we give it an abbreviation of capital J. Now, they made a mistake there. This should say 100,000 joules of sunlight. So they made a pretty big mistake. So 100,000 joules of sunlight. Okay, if 100,000 joules of sunlight hits the grass blades and dandelions and weeds in a field, in an ecosystem, only 10% of that is going to be stored in the glucose molecules. So only 10% of the 100,000 will go ahead and become part of the producers. How do you get 10%? You just knock off, you multiply by 0.1. So 10% of 100,000 is 10,000. So all you do is multiply the previous number, 100,000, times 10% is multiplying by 0.1, and that will equal 10,000. It just knocks off one of the zeros. Then 10% of that 10,000 will be incorporated in the primary consumers. So 10% of 10,000 is knock off a zero, 1,000. And then 10% of that will go on to secondary consumers. So knock off a zero from 1,000, you get 100, etc. So only 10% of that would be 10 joules available for the top predator, the tertiary consumer, the carnivore. So that's why there's fewer carnivores than primary consumers. And they must have miscalculated this one as well, right here, because it's much less than 1%. So 10 out of 100,000 times 100 is the percent that is left for the carnivores, the tertiary consumers, from the original sun's energy that hit the producers, that was taken in by the producers. So 10 times 100 is 1,000 over 100,000. And that comes out to 0.01%. So, whoa, this is much less than they say. So, all the rest of the energy turned into heat. The 99.99% of the sunlight turned into heat by the time it was used by the top of the energy pyramid organisms. Okay, in ecosystems, matter flows through a system while energy is recycled. No, matter and energy flows through the system, but only matter is recycled. Energy does not recycle. You need a constant input of energy from the sun. So the way they have it is false. Food chains are diagrams that follow a single path of energy flow. Yeah, that's true. It's a single organism. A is eaten by organism B is eaten by organism C, etc. Food webs are connected by many different paths. Which of the following facts supports the idea that Earth is an open system with respect to energy? Now, open system means energy is not conserved. Energy comes in a system and then it leaves. Some of it leaves the system as heat. So, Earth emits infrared radiation into space. Well, that shows that it's not a closed system, or else it would have saved all the infrared radiation. Now, infrared radiation is heat. Infrared radiation is equal to heat. So the energy is not conserved or saved. Like the atoms are conserved, but not energy. Earth constantly absorbs sunlight. Yeah, it has to, or else it would run out of energy. And space dust does fall into the Earth, so when meteorites burn up during the meteor showers, the little particles will constantly be falling to the Earth. So that's not a closed system either, because some material is entering the Earth that wasn't there before. But that's not energy. That's not energy, so particles are not energy. So A and B are correct to show that the Earth is open system with respect to energy. So this is the right answer. Energy from sunlight constantly flows into Earth, and heat constantly escapes the Earth. This indicates that Earth is an open system. It's not closed, it's open. There's an open door to leak out energy and to have energy come in. That's an open system, so this is true. As energy flows through the biosphere, producers capture energy from the sun and supply it to the biosphere. Yeah, that's true. Energy is transformed from one form to another. Of course, it's sunlight to glucose covalent bond energy to ATP each of those cases I gave you, also heat was lost. So, all of the above is exactly right. Okay, so let's talk about the molecules that are recycled. Basically, the Earth is a closed system for molecules. We don't really gain any significant molecules from outside our Earth. I talked about the meteor dust. That's really not bringing a whole bunch into the Earth. So we can consider Earth as a closed system for the molecules. Now, if we got hit by an asteroid, well, that adds material to the Earth, but we rarely do. So the elements or molecules are recycled. And we call these biogeochemical cycles because they're molecules important to life, and they're recycled in basically on the Earth. Geology on the Earth's surface. So water is recycled also in the atmosphere. All these have an atmosphere aspect except phosphorus. Well, let's get back to this. These four are essential for life. Our cells primarily are composed of water. That's what the cytoplasm, the cytosol basically is. Then think of blood, and it's mostly water. And the tissue is bathed with water. So very important. Carbon dioxide, also you need water for photosynthesis. It's one of the reactants. Okay, carbon, we already talked about how important that is for building organic molecules. Carbon is a special atom in that it has 4 openings, so in its outer shell, so it can form 4 bonds and make the backbone of large organic molecules. Nitrogen and phosphorus, we have plenty of nitrogen in the air, but it's not available to us. Plants need that nitrogen to make the proteins that we get from eating the animals that get it from the plants. So if the plants couldn't have nitrogen, they wouldn't grow, and the whole ecosystem would collapse. Phosphorus is a very rare but very important element. We already said how it's in our phospholipid membranes. It's part of ATP, amongst other things. So these are very important. And again, we don't get our phosphorus unless we eat plants or animals that have eaten plants. So we're going to talk about the cycles that recycle each of these elements in the biosphere. Okay, the water cycle, you've learned as kids in grade school, I'm sure. But I'll just go quickly through it. Of course, we have surface water, oceans, and salt water. We have rivers and lakes. And the water is also stored as ice and snow on mountaintops and in glaciers or the polar caps. So I don't see any rivers here, but they're there. Fresh water's there. Okay, so this is pretty detailed. So what happens is you get evaporation of the water, the surface water, and then it condenses. It turns into liquid or ice. It can freeze too, but it turns in liquid. That's what condensation is. Forms these clouds. clouds, as they grow, eventually return. They rain down. They do precipitation. That water restores fresh water, and it rains over the ocean too. The water that strikes the land will infiltrate. It will enter the soil, and some of it, if it's a heavy rain, will do surface runoff. You can see it in the street, and that surface runoff goes to the gutters and eventually dumps out into a big source of water, like here, Tampa Bay. So, here's the fresh water. Okay, good. Rivers and ponds. Okay, so where are we? Some water infiltrates. It seeps into the ground, where it's stored in underground lakes called aquifers. That's where people will drill down to get water to irrigate their fields. They'll run a pipe down to where the aquifer is, and then they'll pump it out and irrigate their fields. And that's where the water company gets most of its water as well. Okay, sometimes that water bubbles up in springs. I forgot to tell you that not only does the water evaporate, it also does transpiration. That's when it evaporates out of tiny holes in leaves of plants, leaves. That's what the evaporation water through these little pores in the leaf actually draws the water up through the plant as the water molecules leave the leaves. They pull up, because hydrogen bonding, they pull up water molecules from through the vessels all the way from the roots. The next geochemical cycle, let's talk about nitrogen. Nitrogen, again, is a nutrient very important for plants. Most of the nitrogen in the biosphere is atmospheric. Our atmosphere is, I think, 70% nitrogen. We breathe it, but it doesn't do anything for us. Plants can't use that nitrogen. It has to be changed into a useful form of nitrogen that the plants can absorb through their roots. Okay, so lightning storms will change that nitrogen. The lightning will change that nitrogen into these useful forms that plants can use. Nitrates, NO3. Now, there's also nitrogen-fixing bacteria in the soil that can change the atmospheric nitrogen that diffuses through the soil into ammonium ions. Also, when decomposers break down dead plants and animals, they form ammonium as well. When we pee, we excrete ammonium as well. Okay, so these bacteria that live in the ground are called nitrogen fixers. They turn nitrogen into ammonium, which can then be changed eventually into nitrates that plants can assimilate or absorb through their roots. Okay, there's also nitrifying bacteria that turns ammonium into nitrites and then turns it into nitrates. That is the usable form that plants can easily absorb. Now, there's some kind of plants that actually have nodules on their roots, little bumps on their roots where the nitrogen-fixing bacteria live. So it produces the ammonium that the other bacteria can then convert to nitrates right there in the roots. Such plants are called legumes, like soybeans, peanuts, that kind of crop. Clover. Farmers will do crop rotation, and plant these kind of plants so that they can fertilize the soil with the nitrogen salts that they're forming from nitrogen in the air. Okay, so again, animals get their nitrogen from eating the plants. We can't use nitrogen in the air at all. We rely on the plants for that. I forgot to mention that there are soil bacteria that are called denitrifiers or denitrification bacteria. And what they do is take the useful nitrogen molecules for plants and they convert it back into atmospheric nitrogen. So they do the opposite thing that the nitrogen-fixing bacteria do. So when the soil gets waterlogged, this happens with the denitrifying bacteria. It deprives the soil of the nitrogen nutrients that plants need. Along with phosphate, nitrogen is put into artificial fertilizers to give the plants the phosphate and nitrogen that they need to assimilate to grow and make the crops we depend on. This picture shows the nodules that contain the nitrogen-fixing bacteria. So that plant actually is enriching the soil as bacteria in those nodules are turning the nitrogen into ammonium, which then is turned into nitrates, which is turned into nitrates. Okay, you don't have to know all these different symbols. Okay, so I said soybeans and peanuts, but beans and peas and clover are examples of legumes that have these nodules on the root. Here's another diagram that shows the steps of the nitrogen cycle. Might be a little less confusing for you to study this one. Okay, phosphorus is the second very important thing in fertilizers that plants really need. It's kind of rare because it's locked into rocks and minerals. It's not in the air at all. You can't find phosphorus compounds or phosphorus in the air at all. It's locked in rocks. So when you have weathering of rocks, over the ages, they break down, they flake off, they turn into powder. Maybe erosion does it as well, like wind and water flow. And that phosphorus enters the water. Marine animals, actually plankton absorbs that phosphate in the water and they can make little shells that protects them from it. And again, marine animals eat those microscopic plants, and they get the phosphorus that way, and then bigger marine animals eat those. So phosphorus is really in the water being being recycled in the water, and then when they die, these animals, their bones, their skeletons, and their little shells pile up in the sediment on the bottom of the ocean. And then over geological time, this will be when mountains form. Other parts of the earth are uplifted, and that uplifting could be a plane, like what the state of Florida basically is, a plane from the seafloor being lifted up, plane, or it could be just mountains coming out of the ground. Okay, so then it gets weathered again. It enters into the water stream as it's weathered. Okay, fertilizer also. Fertilizer runs off in rain and enters the water as well. Artificial fertilizer. Okay, again, animals get their phosphorus from the phosphorus in the plants and animals that they eat. The animals that they eat that have phosphorus got it from the plants they ate. Plants get it from phosphorus being in the water that enters into the roots. So once again, phosphorus is important for ATP. You can see the phosphorus in ATP. Also, it's important for phospholipids, of course, which make up the membranes of any cell. Okay, here we have the carbon cycle. So, carbon exists in the air, mainly as carbon dioxide gas. It gets there from several sources, volcanoes. The limestone weathers from it, and limestone is calcium carbonate, and just like calcium phosphate releases phosphate into the water. Well, when limestone weathers, it gives carbon dioxide into the air. The carbon dioxide dissolves in the rain and makes the rain slightly acidic. What else? Respiration from animals returns carbon dioxide to the air. And vegetation has to do respiration as well. So but it's taken by plants. It's taken in by plants by photosynthesis to make glucose. Now, when organic material decays, the bacteria will break down, will do respiration to break down the organic material, and will release carbon dioxide into the soil, some of which becomes filtered out back to the air. same thing's happening in water. Limestone erodes in the water. That limestone, that carbon is used to make calcium carbonate seashells, plankton, and shellfish. And when they die, that calcium carbonate builds up on the bottom sediments of the ocean. Okay, and then that material will get uplifted and exposed in mountains, and that calcium carbonate will return back to the air and to the water again. So there's a cycle there. Of course, photosynthesis uses carbon dioxide, even in algae and phytoplankton. But the fish will return the, I don't see the arrow, the fish will return the carbon dioxide as they do respiration. Okay, obviously they don't show this, but the fossil fuels in the soil sure hold a lot of carbon in the hydrocarbons, in the natural gas, coal, and petroleum that is found down there because all the bodies of dead things that got trapped under soil and compacted before the bacteria could eat them, digest them. Okay, so of course that holds a lot of carbon. Okay, so these numbers that they give you are gigatons per year of carbon. So it kind of quantifies it for us here. So what has the most gigatons per carbon in it, stored in it? Let's see, we got 6,000 for the sediments at the bottom of the ocean. That's big. We got 10,000 for fossil fuels underground. We got 2,300 in the limestone in the soil, or the organic material in the soil. This probably represents both of those things. Let's look at this. When the microbes decompose, they do respiration and release carbon dioxide. That's 60%. I mean, not percent, 60. That's kind of a small number compared to the carbon storehouses that I just mentioned underground and at the bottom of the ocean. Some of that carbon dioxide filters into the land. Small amount, 3 gigatons per year. A lot of it goes back into the ocean, but then to be used by photosynthesizers, algae, but then respiration and decomposition kind of balance out by returning that much. So I guess the surface of the ocean has pretty much, because the phytoplankton want to be close to the surface where the sunlight comes in. Fossil fuels, cement, and stripping land use when you let crop, the part of the crop that you don't pick, when you let that just decay, that puts 9 back into the air of carbon dioxide. Plant respiration does 60. I really don't see animal respiration here, which should be on this chart. So I don't know why they skipped that. Maybe it's insignificant compared to what the plants. Well, plants, there's many more plants than animals, but they should have animals on here. They don't. So 800 is stored in the atmosphere. Gigatons per year is in the atmosphere. Okay, so it's increasing by about 4 gigatons a year because of the fossil fuel imbalancing things. Okay, and us releasing the carbon from where it's hidden in the fossil fuels underground. Okay, so here's some questions. Describe the direction of water molecules during transpiration. Well, transpiration is when it leaves little pores in leaves. It's like evaporation, but it's coming from these little pores in the leaves. So it goes from the plants to the atmosphere. That's transpiration. Water that enters the soil returns to the ocean via what processes? If you look at the water cycle again, water can enter the ocean by flowing off the land. That's called surface runoff. Or it can go through the ground. That's called runoff as well, but not surface runoff. So it can flow into the ocean like that, or it can go seep into the ground, and then it flows out from underground streams. Again, the aquifer would be down here as well. It also flows into the aquifer, but some flows runs off underground into the ocean, some does surface runoff. Both of these are called runoff. So, I'm sorry, but I forgot to talk about the carbon cycle, which is really kind of important because carbon is the molecule that we need to build our organic chemical molecules. So we see atmosphere in the air. They give us actual numbers showing, they give us actual numbers so we can compare. So we have atmospheric carbon. That's in the form of CO2, of course. It enters the air from plant respiration a little bit. When decomposers break down dead things, is released there. It's used up by plants when they do photosynthesis and turns into glucose and starch and wood. Okay, so that's a lot right there. 550. The land picks it up when things die, in the fossil fuel, you can see down here, fossil fuels, there's a whole bunch in the soil because of all dead things. There's a whole bunch. So those are the biggest numbers so far. It enters the ocean where the phytoplankton use it to photosynthesize. They also respire and release it. And things die too. And in the ocean, in the water as well as on land, when they decompose, carbon dioxide is again released into the water, into the air. Some of that carbon dioxide is used to make seashells for plankton and organisms, calcium carbonate, and a whole bunch of it is stored down there as well. So most of the carbon is in the fossil fuel deep underground. And then the next most is in the sediments at the bottom of the ocean, all the seashells piling up and bones. I'm sorry, the seashells actually made of calcium carbonate. The soil, limestone, not just the dead things in the soil, but also limestone is calcium carbonate. It has plenty of carbon in it as well. Okay, and then industry puts out a lot, cars, etc. But compared to all the other things, not really as much, but enough maybe to make a big deal for global warming as the carbon dioxide builds up in the atmosphere. We're adding more than is natural. So let's finally go back to the question. Most carbon is found in what part of the biosphere? Well, is carbon dioxide? No. I mean, 800 compared to these other numbers, the thousands. So it's not mostly in carbon dioxide. In fact, carbon dioxide is a small amount found in the atmosphere. So this is not carbon dioxide. In plants, no. Stored in plant biomass, 550. Less than in the air, even. In fossil fuels, yeah. There's a whole bunch, 10,000, compared to anything else. And then the next biggest would be in the sediments in the ocean. Okay, so I was saying fossil fuels. In glucose, no. Plant biomass, that includes wood and all that, 550. Again, that's not as big numbers as in fossil fuels, 10,000 gigatons. Okay, I should say in fossil fuels and ocean sediments, because they're made of all that calcium carbonate. So limestone in the soil, in the ground, So basically, the ground would be the more general answer. How is carbon returned back to the atmosphere? Yes, that's true. Respiration produces carbon dioxide. Is released during the burning. Yes, that's true. So all the above. Volcanoes, yeah, volcanoes release that and all kinds of other nasty gases. Carbon dioxide releases. All the above is the answer. Animals obtain nitrogen. They only can get it from eating other animals that have eaten plants. So, ingestion of plants or of other animals that have eaten plants. We need it to make our proteins. You can't make proteins without amino acids. Amino acids have a lot of nitrogen in them. I forgot to push the button at the beginning, so let me just tell you what I'm thinking here. Nitrogen fixation is when, right here, nitrogen in the atmosphere is turned into ammonium in the soil, which is then turned into nitrites and nitrates. So it's letter C. Letter A and letter B are the opposites. I forgot to tell you that they're not the nitrogen fixers. They're the denitrification bacteria. They return nitrogen into the atmosphere. So they take the NO3 and nitrites and they convert it back into atmospheric nitrogen, which is opposite of what their nitrogen fixation is about. Those are denitrifiers that do that. And A and B are showing our definitions of what denitrifiers do. Most phosphorus is found in the none hardly is found in the atmosphere in plants and animals, in rocks and sediments. Okay, most of the phosphates in the actual rock. By the way, we mine phosphates in Florida because of all the seashells that are underground, and they add phosphate to the rock. Okay, so